So welcome everyone to our seminar this afternoon. So our speaker is Sheagan John from Texas A&M University. So Sheagan is going to tell us about secondary higher invariants and the cyclic homology for groups of polynomial growth. So please.
So thank you very much for the invitation to speak at the non-commutative geometry seminar. It's much appreciated. And feel free to interrupt at any time if there are any questions. So I just want to go through some of the work that I've been doing over the last year or so. And so I'm hoping to just set some preliminaries and sort of state what the main results have been. And depending on whether or not I have any time left over, at least go through a light sketch of proof for one of these results, and then speak about some future work and sort of related material. So that's going to be the idea. And I suppose since almost everybody here going to be experts in the material, I'm not going to be too laborious with the introductory definitions and so forth. Okay, so let me just set the stage for what is going on. So we're going to be considering closed spin manifold of dimension n and equipped with a positive scalar curvature metric. And then we have our Dirac operator, which sort of captures most or not the vast bulk of the geometric information of such a manifold. Now we have here a higher index or generalization of the Fredholm index in the K-theory class of our reduced group C-star algebra of our fundamental group. So this higher index is taking into account the sort of the symmetries of the space which arise by taking a look at of the action of the fundamental group on the manifold, or rather on the universal cover of our manifold. Now, since we have a positive scalar curvature metric, the Lick-Norwich formula tells us that our higher index class is going to be 0, since it means we have our lifted Dirac operator being invertible. Now, in such a case, when we have a vanishing of this primary invariant, we can still obtain much more subtle topological and geometrical information through some secondary higher invariants. So I want to take a look at 2 of these secondary higher invariants and sort of speak about how we can connect them at some level, and also how we can, well, compute them, as computation of these secondary higher invariants tends to be somewhat of a difficult problem. Okay, so first I'm going to speak about where, in a sense, these invariants are going to live. So I'm going to denote here our equivariant row algebra, equivariant with respect to the fundamental group of M. And we take the operator completion in our, we pick some admissible Hilbert module, we take a look at the space of bounded operators, and we take the star completion of all our, this G, I already have spotted a typo. This G is our Pi1M invariant locally compact operators with finite propagation. So that's our row algebra, and we can, Dr. Yu invented this localization algebra, which is defined as following. We consider all our bounded and uniformly non-continuous maps from the half line to our equivariant row algebra. We impose the condition of propagation tending to 0, and this gives us what is generally much more computable. The K theory then of this algebra is a lot more computable than the K-theory of the row algebra, because we are only taking a look at this finite propagation, this zero propagation condition allows us a lot of computational flexibility. Now, what I'm going to be particularly interested in is this algebra here, which is the kernel of our evaluation map, where our evaluation map, we take the evaluation map of f. So the evaluation map of f is just going to be f at 0. And this forms an ideal of U's localization algebra. Okay, so that's the background, and we'll be taking a look at these two algebras in general. Now, since for the ease of computation of the secondary high invariants that we'll be speaking about, we want to pair elements or in these algebras with cyclic cohomology classes. So I'm just going to quickly recall and define sort of a concrete expression for this cyclic cohomology. And this was first introduced by Alan Kohn. But here I'm going to give, as a very concrete representation. We take the set of all n+1 order linear functionals from the n+1 ordinary tensor product of our group algebra to the complex numbers. I think you can do this with the reals too, but things aren't quite as nice. We have a co-boundary differential. And importantly, so I won't get into exactly how everything is defined, but it's essentially going to act in the same way as the co-boundary differential for Hochschild cohomology. And then we're going to take this T is our essential cyclic operator, which behaves as such. As part of why we call this cyclic cohomology. So when we take the cohomology of a chain of complexes of this kind, we get the cyclic cohomology groups. And we can pair these cyclic co-cycles generally with elements in our algebras. At least that is going to be the intention. Now, something else is to consider delocalized cyclic cohomology groups. And to do this, for every element in our group gamma, generally this is going to be a non-trivial element, but for every element in our group gamma, we now take a look at conjugacy classes. So here, I mean the conjugacy class of gamma, and we can form a subcomplex of our usual group algebra tensor product complex. This time, though, we are only going to look at the functionals which vanish when the product of our basic group elements does not lie in our conjugacy class. So it turns out that this forms a subcomplex, and even better, the very same co-boundary differential that we have here preserves this subcomplex. And so it truly does give us sort of a sub-cohomology group, which we call the delocalized cyclic cohomology groups. Okay, so the first secondary higher invariant that I want to sort of give the background for is the one introduced by John Lott in the early 90s, where under the assumption that we have a fundamental group which is hyperbolic, or we have some non-trivial element and its conjugacy class is of polynomial growth, then he defined this delocalized eta invariant, which is a pairing between traces or zero-dimensional cyclic cohomology classes, as well along with elements, which this ends up lying in our row algebra, our equivariant row algebra. This is a sort of pairing. And so I'll just quickly say that we can do sort of the concrete definition of how our trace acts. If we have kernel operators is as follows. So we're taking our summation over the entire conjugacy class, and it's really because of this that we care about, for example, the growth conditions on our conjugacy class. Now, I think Piazza and Schick, so Piazza and Schick had proved that this does not always converge. So our eta d does not always converge. They had provided a counter example in the case that we do not have invertibility. So invertibility is generally an unnecessary condition. And I'll just mention as well a result of four-author paper. So this is from Shen, Wang, Shi, and Yu, that we do have absolute convergence of this delocalized eta invariant, as long as the spectral gap of D is sufficiently large. So as long as it's sufficiently large, then we don't have to worry about imposing any sort of conditions on our fundamental group. So what I am going to be speaking about here is sort of a higher analog of this delocalized eta invariant, sort of based off Conchern transgression formulas, which I'll define it right after. Okay. So if we want to sort of generalize this from traces, then we can do so. In this case, we'll be considering odd dimensional manifolds. And so all my delocalized cyclic cocycle classes are going to belong to even dimensional cohomology groups. And there's an analog for the odd case, but it's going to be defined a little differently. So we'll define this delocalized higher eta invariant as this integral form. And the key here, as I suppose the first thing that we should ask ourselves is this going to be well defined? So we have two main questions. The first one is, well, is our integrand going to be well defined? Is this integral going to be convergent? And then we might also want to consider, since we are looking at cyclic cocycle classes, we might also ask ourselves, well, does this depend on the representative of our cyclic cocycle class? So these are all questions that need to be answered in order to make full sense of this. Okay, so that's the delocalized higher eta invariant. And before I sort of go any further with it, I want to switch now to the second kind of secondary higher invariant, and that is the higher row invariant introduced by Higson and Rowe. Not, I think, initially in terms of a class in the K theory of the evaluation ideal of useful localization algebra, but it can be recognized as such class. So it's a K theory class, a concrete K theory class in this localization algebra ideal, where our n is going to be the dimension of our manifold. So now we want to do something similar with the secondary higher row invariant, and that is pair it with cyclic cohomology. So we do something similar. Here I'm using the determinant map that Shi and Yu defined in the case for traces. And that is, we can, if we have a suitably constructed representative of this row invariant class, then we define our determinant map, which is just a linear map of a K theory, like this, as this integral. Now, so you immediately see certain similarities between the two. And in fact, that's part of what we want to investigate. That is, just how far do these similarities hold? Can we perhaps express our constant character pairing here in terms of our
I just want to make a small comment. I just want to point out this determined map origin actually goes back to Scandalis and Delocalized.
Yes, I should have mentioned that. Yes, it does. Thank you. Okay. Right, so we want to ask ourselves, does these similarities that we see, how far do they extend? Can we perhaps express one in terms of the other? May there be times that one is well defined and the other is not, one convergent, the other is not, so forth. So the main theorem, or my main result then, is going to be the following: that if we have a closed or dimensional spin manifold, equip it with a positive scalar metric, and we put a particular growth condition on the fundamental group, that is, we have the fundamental group being virtually nilpotent, or as proved by Gromov, that's the same as it being of polynomial growth, then both our delocalized higher eta invariant, as well as our constraints pairing with the higher row invariant, converge absolutely. Moreover, when there we have this equivalence of the two pairings, so we can express one in terms of the other. Now, this here is a pretty crucial point, and it's largely what I'm going to be speaking about in this talk. That is, how do we truly exploit this virtual nilpotency? So I'll just remind that all this means is our group has a normal subgroup, or which is nilpotent and which is of finite index. Okay, so that's the main theorem. And we have analogous results proven by Shen Wang, Shen Yu, when the fundamental group is hyperbolic. I should just quickly mention that these are going to be discrete countable groups. So the hyperbolic case uses quite some similar, but in some cases, quite different techniques from the virtually nilpotent case, just by their very geometric nature. And if time permits, I'll also want to speak about what happens when we move away from the realm of hyperbolic and virtually nilpotent groups. If we can still say something so strong, even though we might lack a lot of the geometric information which these two classes of groups provide. Okay, so the first problem, and one which I had mentioned before, is that naively our delocalized cyclic cocycle classes are defined for our group algebra. So if we want the sort of definitions here and here to make any sense, we need to show that these cyclic cocycles extend continuously to our row algebra and to our evaluation ideal of the localization algebra. And it's sufficient to show that they extend continuously to certain smooth, dense subalgebras. So, in particularly to their projective tensor, their n+1-fold projective tensor norm, which introduces just a little bit of extra details. So I'll just mention that in my particular case, where are we? So this algebra is essentially the algebra which was created by Kohn and Moscovici, which uses certain rapid decay matrix elements. And then this one is from Sheagan John. So I'm making use of these two algebras, showing that in the case of virtual nilpotence, we have the ability to extend our cyclic cocycles continuously. And these are quite specific, I will say, these are quite specific to the case of polynomial growth or virtually nilpotent fundamental groups. If we don't have this condition, then we need to search for completely different smooth, dense subalgebras, and that's generally a very technical and subtle issue. Now, the extension itself, along with the convergence of the integrals, depends crucially on the growth properties of the cocycles. And this growth property of the cocycles, in turn, depends crucially on the virtual nilpotence property of the group itself. So I want to sort of give a little sketch of how we use this virtual nilpotency. And to start with, we need to know what sort of growth conditions we are interested in. So we say that our group is a polynomial cohomology if for any element in, well, any cocycle in our group cohomology. So this is just standard group cohomology here. That there exists technically a skew cocycle, so that we can, for certain technical reasons, that there exists a skew cocycle such that the two classes are the same and gamma psi is of polynomial growth. And by polynomial growth, we just mean that when we take the absolute value of our co-cycle applied to group elements, it's bounded by some polynomial in terms of the norm on our group. So this is just is a norm on gamma induced by a length function. And we don't really care about which length function, since we have a nice quasi-isometry property. Okay, so that allows us to generalize this notion of polynomial cohomology to polynomially bounded. And so we say so a second main result or supporting result here is that if we have gamma, which is a virtually nilpotent group, and we take any delocalized cyclic co-cycle class, then it's going to have a representative of polynomial growth. And in such a case, we say that our delocalized cyclic cohomology is polynomially bounded. So I would like to spend a little while just sort of giving a very brief outline of this proof, because in some sense, everything else follows from it, but everything else is a bit more standard. Okay, so we start with a theorem of Buglia and Nestor. Buglia proved this topologically, Nestor to algebraic means of a splitting of our cyclic cohomology in terms of delocalized classes. And then importantly, isomorphisms between our delocalized cyclic cohomology and group cohomology of n gamma. And I'll just remind everybody what n gamma is. So n gamma is the quotient of our centralizer of gamma element. So we take the centralizer of this element and we quotient out by the cyclic group generated by gamma. And we have two cases to consider, gamma being of infinite order and gamma being torsion. And it'll turn out in our case that this matters quite a bit. We only want, the proof depends quite heavily on us being able to throw out any infinite order contributions to our delocalized cyclic cohomology. So I'll make an, oops. So I'll make a note here that if gamma is virtually nilpotent, then so z gamma and n gamma. And our second point here, and this is a theorem of G, which states that if we have any group gamma, and we take a look at this group cohomology, that this is polynomially or the polynomial cohomology for gamma virtually nilpotent. So we use these ingredients to sort of see how we can show that what we have on our left-hand side is polynomial cohomology as well. Now the tricky part here is that simply having an isomorphism does not tell us whether our isomorphism preserves the growth conditions on our cyclic co-cycles. This is to actually show this, we need to have a much more detailed geometric argument. So the isomorphisms simply give us a clue as to how we might approach this. And so I will start with this, that following the idea of lot. So following the idea of lot, we can express our cyclic co-cycle, so our delocalized cyclic co-cycle, in a special form and use a cohomology group H star C. So this here is just a cohomology group which is built to be particularly useful, and there's a one-to-one correspondence between our delocalized cyclic co-cycles and when we express them in this special form. And then, so that's sort of our step one. And then we want to form a larger complex. So we form related, so let's just say that, a related cohomology group, let's call it D. We form a larger cohomology or related cohomology group which captures, in a sense, the centralizer information. And I'll make that more precise later. So the point here is, in this one, we write it in such a way that it captures the information from n gamma. And here we write it in such a way that it captures the information from z gamma. Okay, so how do we use this in practice? Well, we know from G that if we have virtual nilpotents, that we have polynomial cohomology. So we already know that H n gamma and H n Z gamma. So this is our group cohomology, polynomially bounded. And we want to use this and exploit it in such a way to show that this side here is polynomially bounded. And the first thing that we want to do is construct a growth preserving isomorphism between our two special cohomology complexes, which in some sense is going to be the first step in bridging, showing that there's a growth preserving isomorphism which captures this N gamma information and one which captures this V gamma information. Now this growth preserving isomorphism its existence is quite dependent upon, as I mentioned before, gamma of infinite order not contributing to this cyclic cohomology. And so I will just note that, again, using a theorem of G, in a later paper of his, he proved that for gamma virtually nilpotent, we can exploit certain cohomological dimension results, and therefore our does not contribute to the delocalized cyclic cohomology. Not in the sense that we, in some technical sense. Okay, so once we have these set up, then the real technical difficulty comes in showing the following, that we can express this H, these special constructions in ways which link them all the way back to something we know is a polynomial cohomology. That is this. This is something that we know by G's result, and we want to exhibit a chain of isomorphisms which take us all the way from HC to our group cohomology here. And so what we want to do is exploit classifying spaces, So we work from one end and say, well, we can write our group cohomology in terms of the topological singular cohomology of our classifying space for this group. And then we can write it in terms of a certain balanced product involving our total space. And the nice thing about this is that we can do the same thing for this group here. Write it in terms of a total space depending on gamma and Z gamma. And so what it boils down to is to do the following, is to exhibit a growth preserving isomorphism between these two spaces. And this is all going to be singular cohomology. So we need to be a little careful about what we mean by polynomial growth here. But we can be, if we were careful, then we can exploit the notion afforded to us and so it's this that we want to do. Can we exhibit a growth preserving isomorphism between the two? And I wouldn't go through any, I suppose, further details about this, but this is a not entirely trivial thing to do. But once it is accomplished that we can in fact exhibit such a growth preserving isomorphism, then we have, as it were, our final chain of isomorphisms, and I'll just sort of detail what each one is. So we know our group cohomology here is just going to be our topological, our singular cohomology on this balanced product. And we have already shown that we have a growth preserving isomorphism psi between the two. And so then this psi is going to be the same psi, which is now going to be between our group cohomology of Z gamma and our cohomology group, this special cohomology group here. So it just immediately descends because of these equalities. So that's our first isomorphism. And then between these two, we do have an isomorphism. This A, I'll just write A is the order, ends up being the order of gamma times the order of gamma plus 1 over 2. So A is just some rational number. And actually, this is the reason why we have to do tensoring with the rationals. So this isomorphism holds in rational cohomology, not necessarily in integral cohomology, but rational cohomology is all we need. And in fact, G's theorem here is precisely about exploiting rational cohomological dimension. So everything here is done rationally. So we have very explicit isomorphisms. R is a very explicit map from this part to this part. And so we have extremely explicit growth preserving isomorphisms, and then we simply compose them. And well, now we have explicit growth preserving isomorphisms from our group cohomology, which we know is already polynomially bounded to this rational tensor with our H and C, which we know is going to be the same as our delocalized cyclic cohomology. And that gives us the result that we are interested in. So quite algebraic topological in nature. I suppose one of the beauties of non-commutative geometries that you end up finding yourself doing a whole host of various things, operator theory to functional analysis to pure algebraic topology. And once we have this result, then the rest follows quite naturally. So the extension to smooth dense sub-algebras the fact that our pairings are independent of representatives, co-cycle representatives, and just the overall convergence of our integrals is then a mixture of using this result and a lot of rather technical work on finite propagation and functional analysis estimates, norm estimates, and so forth. But once we have this result, which is sort of the key to, I suppose, making sure everything else follows through properly. Okay, so I think I just have a few minutes left. So I just want to very quickly make a note on something which I've been thinking about, and sort of the first thing is to me is, well, what happens when we change our group? So in other words, what happens for our fundamental group not hyperbolic or virtually nilpotent? And so, as I mentioned before, Shan Wang, Shen, and Yu had proven that for lots delocalized eta invariant, we don't need any growth conditions on our group whatsoever. But for a lot of if we don't have this suitably large spectral gap, then we still end up caring quite a lot about how these groups behave. And one question that we may ask ourselves is, well, if we were given a manifold M by N, just a sort of product manifold with the fundamental group of M hyperbolic and the fundamental group of N virtually nilpotent, then could we say, do we have similar results regarding the pairing of the higher row invariant? Do we have similar results regarding the delocalized higher eta invariant? And this is, in this case, this is something I'm currently working on with Alexander Weygand. But another, perhaps more difficult question is, well, what happens when we don't have hyperbolicity or virtually nilpotence at all? And a good set of groups to consider are actually quite usual counter examples in geometric group theory and algebra. And that is, what if Pi1M is a non-solvable bomb/solitaire group? And this is a bit more of a tricky question. I'll just quickly remind everyone what the bomb/solitar groups are. So very easily described in terms of you have two generators and they satisfy this relation. But fiendishly difficult groups to generally get a handle on, and they tend to destroy a lot of conjectures in geometry and algebra. And why I would want to think about these is, well, if we have a bomb/solitar group which is non-solvable, so we throw out the nice ones like the integers, for example, these cannot embed in any hyperbolic group. So we have no non-degenerate morphism from these to any hyperbolic group. Once we throw out the solvable groups, they're always going to be of exponential growth. If they are of exponential growth, then they can't be virtually nilpotent. So we completely move away from the hyperbolic and virtually nilpotent worlds. And I would guess that even if this question makes any deeper sense, then probably we need some new tools in order to consider pairings, because, and why I say if the question makes any sense, is we do need to ask ourselves the following topological consideration, and that is, can Pi1m be bomb/solitar, again, non-solvable for M, a closed spin manifold? And this to me is not entirely obvious yet. We know that if we are in dimension 4 and above, that we can take a CW complex and we can construct it in such a way that we can get the fundamental group to be anything that we want. But such a CW complex is not at all on the nose as a spin as a manifold, much less as a closed spin manifold. And so that's a very important topological consideration if we think about bomb/solitar groups. I'll just mention as a last remark that I think it was in the early 2000s that Peter Challen showed remarkably that if we have a non-solvable bomb/solitar group, that there's no non-degenerate morphism from it into the fundamental group of any closed 3-manifold. So we already have to throw out all 3 manifolds as possibilities for that and look at higher dimensions. Okay, so I think I will stop here, and I thank you all for listening.
Okay. So thank you. Do you have any questions or comments?
Yes, actually, could I ask something?
Yeah, please, Jonathan.
Actually, with regard to what you said at the end, it's sort of obvious that any finitely presented group can be the fundamental group of a closed spin manifold of positive scalar curvature, but you don't get necessarily very interesting manifolds that way, just because you can take a sort of stupid example and then take a product with something else, say with a sphere, and then the product will always have say positive scalar curvature. So that I don't think that by itself is very much of a question, but the more interesting question is, are there any interesting geometric applications of this theory that you know of? In other words, what do you said at the beginning that these invariants are hard to compute.
Right.
Are there any cases where you can compute them and where they tell you anything that might be interesting?
Right, right. So yes, I suppose that I should specify that I'm sort of thinking about more naturally occurring closed spin manifolds than those purposefully cooked up to satisfy this condition. So in the case where is there something that we can tell about the secondary higher invariants when we compute them? Well, one of the, I suppose, important examples is perhaps if we have our highest row invariant, it depends on our metric, and the way it's defined, we can sort of tell, for example, if we are able to deform one metric of positive scalar curvature into another through a homotopy class, which is completely residing within our space of positive scalar curvature metrics, which is not something that our higher index class by itself has the subtlety to do. Does that sort of answer or give an answer to your question?
Not exactly, because the question is, can you still get any interesting examples where you need these higher index classes where the more accessible invariants like the lot invariant are not enough?
Ah, I see. Where we need to pair with these higher cyclic cocycles. Is that the question?
Yes, that's right.
Oh, I see. Okay. So that is a very, very good question. I don't have any off the top of my head examples right now, but I would probably say that in a sense, analogously to how very many obstructions, such as, let's say, Stiefel-Whitney classes in regular singular cohomology, are really only detectable at the higher cohomology groups. It's something that we might expect to see here too for these higher analogs. That certain obstructions are not going to be determined by the trace classes, but they're going to be determined by these higher ones, because the obstructions in some sense live in higher, or analogously to living in higher cohomology groups. Again, similar to Stiefel-Whitney classes in H2 being obstructions to a manifold having spin. But I don't have off the top of my head any concrete.
Well, maybe let me make a small comment. So maybe to Jonathan's question. So if, for example, if let's say, take the case of the class of groups that Sheagan's talking about, polynomial growth or even hyperbolic groups, since bound cone is known. So for these positive scalar curvature questions, the higher indices or the higher row elements do provide more information when it comes to if you want to say, the size of the positive scalar curvature matrix space or higher homotopy groups of this space. If you want to consider its rank and so on and so forth, it's going to give you a more precise lower bound of these sort of things, as opposed to just the delocalized, which is just the trace. So yeah, for these classes, in general, if you know the Novikov is true for these groups, then yeah, you can get a better estimate on these homotopy groups of the space of positive scalar curvatures on a manifold.
Yeah, another related application might be to the structure group. I mean, like a similar, like estimate.
Jonathan, are you speaking? I think you are muted.
Oh, I think I'm not muted. You cannot hear me?
I can hear you, but Jonathan, I thought, was Jonathan, were you speaking?
No, I didn't say anything.
Okay. Yeah, so indeed, it can give you more information.
Yeah, I guess one point for this kind of application, you have to make sure that the information is coming from the case theory of the sister algebra.
Mm-hmm.
So this, in essence, is giving one, like computing those case-theoretic secondary invariants rationally. You know? I mean, those sister algebra invariants. Okay, so any other question or comments?
Can I just ask a question about your growth condition on your group? Would it be enough to just impose a growth condition on just the conjugacy class? So say the conjugacy class is polynomial growth instead of the whole group?
No, I don't think so. So or at least for the case of traces, yes, one can do so. But for our higher, so let me probably go here. Where is it? Cyclic. Right. So in a sense, we are considering all our conjugacy classes. So do you mean that we impose growth conditions on every single conjugacy class, or just for the gamma that we are interested in?
So I guess you have a result that depends on one conjugacy class. So would that result be true if only the conjugacy class is polynomial growth, not the whole group?
Okay. But because, so we want to, if we, for the higher case, the proof itself, at least the way that that I did it, there seemed to be quite a bit of interrelation between the various dimensions of our delocalized cyclic co-cycle complexes. So when we were considering boundary conditions, for example, had to adjust the dimension, that's a good question, but it was at least somewhat important that we have the full power of gamma being virtually nilpotent, and the main reason for this is as follows: if we don't have that, gamma being virtually nilpotent, then we don't really have that this is a polynomial cohomology. I can't use G's result that we have polynomial cohomology. And notice that this result uses the entirety of gamma. It's not specific to any one conjugacy class, but in the proof of showing that even one conjugacy class was polynomially bounded, I needed to use the full might of this result. And so in some way, we are taking, or we needed to take into account the entirety of gamma's growth condition and not just each element in gamma. because
Okay.
then this result where we take a look at the total class, the total space E gamma, it doesn't really have any analog if we only consider individual conjugacy classes of polynomial growth.
Okay, thank you.
Any other questions or comments for Sheagan? Okay, so let's thank Sheagan again for a nice talk.